Today we will discuss the continuity equation for the fluid. This continuity equation is the another form of the conservation of mass. So this continuity equation is based on the conservation of mass. In case of the fluid flow, conservation of mass is applicable for a controlled volume. So what exactly it means is that in case if any pipe or channel through which the fluid is flowing, and if we consider any uh, controlled volume, let's say this is the controlled volume under which we are considering. So whatever the fluid you are getting as an inflow, the same amount of flow you will get it as a outflow. So considering this principle, we will try to derive the equation of continuity for the fluid flow. For this purpose, we are considering that there is a pipe, and this pipe has a varying cross section such that fluid is flowing in this direction. So this is your direction of fluid flow, and we are considering the two section of this pipe, where let's say this is section is A dash, and this section is B dash. What we are assuming that the cross section at this AA dash is A1. However, the cross section at section BB dash is 8. We are assuming that the velocity of flow at this location is V1 and velocity of flow at this location is V2. Now, another important thing we are considering that density of the fluid at this section is ρ1 and density of fluid at this section is ρ2. So applying the conservation of the mass at section 1, so the rate of flow at section AA dash, rate of flow at section AA dash, we can write that the fluid flow is rate of flow is ρ1 into A1 into V1. Area into velocity, this particular thing is giving us the volume which is flowing through per second. However, once we are multiplying with the density of the fluid at this section, this will giving you the mass flow per second at the section of A dash. And similarly, using the same scenario, we can write the rate of flow for section BB dash will be ρ2, which is the density of the fluid at section BB dash multiplied by the area of cross section, that is A2, and the velocity we have considered is V2. This particular section follows the law of conservation of mass. So according to the law of conservation of mass, we can write that the rate of flow at section AA, rate of flow at section AA dash will be the rate of flow at section BB dash. Rate we are having at section AA dash is ρ1 multiplied by A1 multiplied by V1 is equal to ρ2 A2 V2. This is the continuity equation. Once we have considered that density of the fluid at two sections are also varying. So if we are considering a special consideration when this is an incompressible fluid flow, then at both sections the density will be the same, and we can say like this one. So we can modify the equation 1 as rho A1 V1 is equal to rho A2 V2. So we can write A1 V1 is equal to A2 V2. So for a incompressible fluid flow, the continuity equation look like this one. Now the equation which is shown in equation 2 can be rewritten in that form, where A1 divided by A2 will be equal to V2 divided by V1. So if it take any problem such that section 1 and section 2, so it is having a converging cross section. This is A1, this is A2, then A1 by A2 will be definitely greater than 1. It shows that V2 minus V1 will also be greater than 1. That means V2 will be greater than 1. So if this is a converging type of area, then definitely at this section velocity that will be higher than the velocity at this section. Now let's try to solve some problem based on the continuity equation. Now the problem we are going to solve is like that. A 30 centimeter dia pipe conveying oil branches into two pipes of dia 20 centimeter and 15 centimeter respectively. If the average velocity in the 30 centimeter dia pipe is 2.5 centimeter per second. So first question is find the discharge in the pipe. Second question is determine the velocity in the 15 centimeter dia pipe if the average velocity in 20 centimeter dia pipe is 2 meter per second. So let's draw the figure corresponding to this question. So 30 centimeter dia pipe is here, where D1 is 30 centimeter and the velocity, average velocity we are getting in this pipe is 2.5 meter per second. However, this branches into two parts. So let's say this is section 1 and this is pipe section 2 and this is section 3. So in this section the pipe diameter is 20 centimeter. However, the velocity we are getting in this is 2 meter per second, and in this section the diameter of pipe is given as 15 centimeter. However, we need to figure out the velocity in this section. So first of all, we'll quickly write the continuity equation for this one. Let's consider this section. So cross sectional area, if this section, let's say this is A1, so A1 is pi by 4 D1 square. So that is pi by 4. Let's take all the units in meter. So this is 0.3 meter, 0.3 square, and this comes out to be 0.07068 meter square. Similarly, we are taking this section as section 2. So the area of cross section 2 is pi by 4 d2 square, that is pi by 4. d2 is given as 0.2 meter square, so that comes out to be 0.0314 meter square. And this is your cross section A3. This is A1, A2, A3. Similarly, A3 is pi by 4 D3 square, and that is pi by 4 multiplied by 0.15 square. That comes out to be 0.01767 meter square. So first section of this problem asks for charge in pipe 1 is, let's say this is Q1. So this can be written as that this charge is Q1 is equal to A1 into V1. So V1 is given to us 0.017 0.068 is the area, and the velocity in this section is 2.5 meter per second, and this value comes out to be 0.1767 meter cube per second. So this much cubic meter of oil is flowing per second through this pipe in pipe 1. Now the second question, which asks for the value of or the velocity in the pipe 3. So we can say that we have to figure out the V3. So if we rewrite the continuous equation for this section, so the discharge at section 1 is q1 and that will be equal to the discharge at section 2 plus discharge at section 3. So we can write that a1 v1 is the cross section discharge at section 1, and similarly this will be a2 v2 plus a3 v3. So if we look at this equation, out of 6 parameters 5 are known, only this v3 needs to be figured out. So let's quickly put all the numerical values in order to get the v3. So we just figure out that this is 0.1767, this equals to a2 is 0.0314 and velocity is 2, plus a3 is q3 is 0.01767 v3. So v3 is equal to, if we solve this thing, so this comes out to be 0.1139 divided by 0.01767, and that will give us a value of 6.44 meter per second. So this is our answer. So in this section, this V3, which was unknown to us, is now known to us, that is 6.44 meter per second. So that's all for today's discussion. If you have any queries, drop your queries in the comment section. Thank you.